Hello everyone and welcome to this new session in which we're gonna go under the hood and understand exactly what goes on when we call on this fit method right here. In fact, we're gonna be training our own model without making use of this fit method. So here we're gonna have this custom training loop which we're gonna build. As you can see here, we have this training block, we have this validation block, and then we have this method which we named neural learn. And this method which replaces the fit method which we used to get in. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. TensorFlow is not only a great machine learning library because it permits us build and deploy machine learning models. Its greatness also comes from the fact that it permits us build these models and train them without getting to know everything which is going on under the hood. So all you need to do to train a TensorFlow model is to specify that model and then make use of this fit method while passing in your data set, which is made of the inputs and the output. That said, in this section, we'll see how to create our own fit method. That is, we'll go a step further in understanding how TensorFlow works under the hood. Recall that when you make use of this fit method right here, what goes on essentially is TensorFlow applies the gradient descent method to update this weight theta right here. So all these thetas are being updated until the model converges. Recall that for given inputs x1, x2 and outputs y1, y2, y3, our aim is to update this weights such that when we pass in these inputs into the model, we get an output right here which looks practically the same as this outputs. And to know whether this model outputs are the same or similar to this actual outputs, we apply or make use of a loss function which computes the difference between these two. And generally, initially, when you start training the model, that's when you start updating these parameters, there will be a great difference between these two. But as you keep on updating these parameters, we notice that the loss starts dropping. And so once this loss drops until it converges, we then stop the training. But recall also that the way we update these weights is such that we take the initial weight minus the learning rate, which is a constant we define, times the partial derivative of this loss. Now the loss, which we've seen here, which we understand that is the difference between the model's predictions and the actual prediction. So here we have this partial derivative of the loss with respect to the parameter or the weight in question. And so if we want to update, say, this theta double prime to 1, we'll simply use this same approach. Now, the way TensorFlow computes this partial derivative right here is by automatic differentiation. And so when you have this model with the inputs, as these inputs are being passed into the model in this forward pass, right up to the output, TensorFlow records this gradients or this partial derivatives, and this is done for each and every parameter such that once we get the output and we compute the loss, we could now get this whole partial derivative right here, that is the partial derivative of the loss with respect to each and every weight, and then each and every weight is being optimized or being updated via this formula. So in general, we can have theta whatever, and then we have let's say ij. We could have I comma j equal theta I comma j minus learning rate times partial derivative of the loss with respect to theta ij. And so as we go through this forward pass, what TensorFlow does is it keeps in mind the thetas and their gradients. Let's call these gradients the theta. So we have the theta and the theta which have been stored or which have been recorded as we go through this model that's in this forward pass. that process of recording these gradients here as we pass in our inputs in the model is similar to what we would have with a tape recorder, where here you just need to speak in this mic, the information is recorded, and then it could be replayed later on. And so here, as information has been passed in this model, these gradients are being stored and they could be used in the gradient descent algorithm later on. Getting back to the code, we'll now see how to build a fit method from scratch. So here we have this. Let's have for epoch in epochs. You see that now, unlike here where we just needed to pass in this number of epochs and TensorFlow does the job, here you really need to do much work on your own. Okay, so we have for epoch in epochs. What we're gonna do here is go through each and every batch of our data set. So we also have that's for each epoch, we are now going to go through each and every batch. So for X batch, Y batch, in train data set, let's have this tuple. So we have X batch, Y batch in train data set. What we're gonna do now is pass in this X batch into our model, and then after getting the model output, compare that model output with the actual output and obtain the loss. So here we have ypred, which is what the model outputs. We have the model. Here we've defined the model already. So we're working with a sequential model we had built previously. Here we go. We have this sequential model. And then in this model, we're going to pass our X batch. There we go. We specify that we're training. So in training mode, training equal true. Okay, so now we have ypred, and what we could do next is compute the loss. So here we have loss equal loss function, which we're going to define loss function, which is going to take in our ypred and the models and the actual y. So we can make use of this custom BCE right here. Now this takes in the y true, ypred. So we should ensure that we have y true before ypred. And here we should have y batch and then ypred. Okay, so let's take this off, and that's it. So here we're gonna use our custom BCE. We could take this off and then specify custom BCE. Now we have our custom BCE. We could go ahead and update this model's weights. But in order to update our model's weights, we need those gradients. The way we get those gradients is by recording or taping these gradients as we pass the input into the model. To do this, this part of our code has to be put in a particular scope. So here we have with gradient or tf.GradientTape as tape. We are going to have this. Let's have that. We are going to have this 2 lines of code. Now the effect of doing this is we are recording the gradients in this tape or in this recorder. We could say this as recorder. And now all the intermediate values of tether and intermediate gradients have been recorded and now could be used in computing this partial derivative right here. That said, we can now obtain the partial derivatives. So we have partial derivatives equal the tape. So this tape, or rather equal the recorder, because we changed that to recorder. So equal this recorder dot gradient of the loss with respect to all the model's trainable weights. And so this line of code here represents this operation, that is computing this partial derivative of the loss with respect to each and every weight. Then we move on to optimize our model by going through this stochastic gradient descent or some other gradient descent based optimizer like the Adam optimizer, which we've used so far. That said, we get back up to this compiler. We have this optimizer. Let's take this from here, copy that, and then what we'll do is we are going to add a cell. Let's take this up. We have our optimizer here. So let's have this optimizer. That's it. Our item optimizer defined. We run that cell. Okay. And then what we do now is we have optimizer dot apply gradients. So we use this apply gradients method in order to update the weights based on the gradient descent algorithm. In here we have zip of gradients, or rather the partial derivatives. So we are passing in the partial derivatives and the model trainable weights. So recall we have some untrainable weights actually. So we have this model trainable weights right here and the derivatives. Let's scroll. Okay, let's have this here. This is linked, so this part is linked to this, and then for this it's the whole algorithm, the whole gradient descent based algorithm, which takes in this partial derivative and the model trainable weights, that's the tethers. Obviously, while defining the optimizer, we have already set the learning rate, so there we go. Then from here we could print out our loss values. Here we could print out the loss, print off the loss. Okay, so now we're set. We could now run this and see how this works. Let's not forget to specify the number of epochs. So let's have number of epochs equals, say, 3 for stat. Let's have this epochs, and then we run the cell. We are told here that the model is not defined, so let's modify this and have Lunette model. Run that again. We get in this error where we told this expects the shape, while what we get is this. Now the fact that we have this means that we haven't yet resized our training data. So let's get back up and then run this cells here for resizing, and there we go. Let's run the cells. Okay, we have that, and now it looks fine. Okay, so we have the cells run. Let's get back to our custom training loop. Okay, so let's run this. As we can see, the training goes on smoothly. You have those loss values which are dropping, and we run this actually for 3 epochs. So there we go. We have our loss which is dropping. And then we could decide to print this out after a given number of steps. So here we could add the step and enumerate. There we go. We could check out our free Python course on neurallearn.ai to understand this in case you're new to all these keywords. So there we go. We enumerate, we have step, and then what we're gonna do here is we're gonna print our loss values only after a certain number of steps. So given that we have 689 steps, that's if our batch size is 32, we would suppose that after, say, 300 steps, we're going to print this loss out. So here we're going to have if the step modulo 300 equals 0, then we'll do the printing. So there we go. We have this print. And then for every epoch stat, we're going to print out training starts for epoch number, and then we format that. So here we have the epoch. Okay, let's rerun this again. Here's what we get now. So we have this training starts, and then we have this intermediate loss values which have been printed out. Now what if we include the validation? So here, notice we finish, like we train the model, and then after training for 1 epoch, we then get into validation. So for X, batch val, Y, batch val in val data set, we'll simply copy this out. So here we have this here. Let's paste it out here. Okay, so here we have the Y pred and our loss val. It's still the same model, but here training is set to false. We have training false, we have Y pred val, and then we have Y batch val. Here's X batch val too. And then we print out the loss val. So here we have validation loss. Okay, let's run the cell now. While training is going on, we could include the metric. Here we have this metric.
which is binary accuracy. Now while training is going on, we could deal with a metric. So here for this, or for each batch we're working with, we are gonna update the state, we are gonna print out the result, and then we are gonna reset the states. So let's get back to this part, and then just after this, that's for this particular batch, what we have here is we have our metric dot update state, and then we pass in our y, or our y batch, that's our y batch, true y, and then y pred. So once we update this metric, we could now print out this metric value out of this for loop. So after each epoch, we're going to print out the metric value. And so here we have print of metric dot result. There we go, print metric dot results, and then we should have here the accuracy is. There we go, accuracy is, that's it. Once we print out the result, we now go ahead and reset states. So we have metric dot reset states, and that should be good. So we reset the states, and that's fine. We could repeat this exact same process for the validation. With the validation, just in here in this batch, we are gonna repeat the same step. So here we have the metric, let's paste it out here, and then here we're gonna have metric val. We update the states. Here we're gonna use y batch val and y pred val. Okay, once we update the state, we now do this same process here. So we print and then we reset the states. Let's have this here, print and then reset states. Let's take that off. Okay, so we have here metric val and then metric val, and that's it. Let's define metric and metric val. Here we go, we have metric and then we have metric val. So that's it. So here we see how to recreate this fit method that we have here. Now that we've seen this, we see the training is going out well. We see the training loss, the validation loss, and that's it. But the training loss we're getting here is for the, each and every 300th batch. So let's take this off from here. Let's say we print this out after each epoch. So the training loss, we print it out after each epoch, and that's it. This means that we don't really need to have this again. Let's take that off. So we print out the training loss and the accuracy. This should be good. We now run this, and here's what we get. You see, we have the train loss, we have the train accuracy, validation accuracy. We've changed this to val accuracy, and then we have the validation loss. Then for epoch 2, we have the same. For epoch 3, we have this. For now, we're in the eager mode, so obviously this training process is going to be slower as compared to if we're working in the graph mode. Now what we're going to do is we are going to pick out those computation expensive units of this cell right here. Now we know that this is computationally expensive because here we have to pass in our input into the model, compare this output, compute the loss, get the gradients, optimize the model, update the metrics. So we look at this as one of those blocks, and then we have this other block. Let's scroll up. We have this. Let's take this off. So here we have this block, and then we also have this other block. Now you'll notice that this is what we call the training step, and then this is the validation step. So what we could simply do here is create this two methods. So we have train, let's call this training block. We have the training block, and then what goes on this training block is we take in a x. So you have x batch and then y batch. Basically we just copying all this. So here we copy this, let's cut that, and then we paste it right here. Okay, so here we have this training block, and then here instead of having this, we just say for each step we're gonna go pass through the training block. We pass in x batch and y batch. Then we repeat the same process for the validation. Here we have this copied out, and let's copy this. Okay, so here we have the validation block, or let's say val block. Here we have the val block, which takes L batch val and Y batch val. There we go. We have this train block, validation block. Now just here we could paste out. Let's create our validation block and then take X batch val, X batch val, Y batch val. There we go. We paste this out. So for this, we have that. Now since we compute this loss in the training block, we want to return this loss. So we return this loss. Okay, we have the loss returned, and then just right in here we're gonna say loss equal this. So we call this loss, and now we could make use of it right here. And then we do same for the validation block. With the validation block, we take this here and then we return our loss val. Now that sounds great. We should now be able to change this in our graph mode. So we have tf function. That's all it takes to convert this to graph mode. Tf function. That's it. So there we go. We've converted this to graph mode. We can now run this. We're getting this error. Let's check on what's going on. Okay, let's run this now. We told on indent doesn't match any outer indentation level. Okay, yeah, we should put this to match up with this width, and that should be good. Let's make sure we don't have the same error here. So we have this 4 and that's it. Okay, so let's run again, and obviously we should have no problem. Now we could retrain our model and we should get faster training this time around. But still we getting this error. Loss val must be defined before the loop. So we get back to the code, and what we could do is comment this section which is for the training, because this works already. So let's comment the section and then focus on the validation block. The first remark we have here is we've made an error of putting this for loop in this val block. It's not actually a syntax error, but more of a design error. So it's better for us to have this val block in this for loop instead. So that said, we're going to cut out this from this val block, and then what we'll have here now is for this. So we have for x, y in the val data set. You see, we're going to pass this in here and then have this val block. So here we have this val block now. Everything looks fine. We should have that. And then let's now run the cell again. You now see how just recorrecting that error automatically solves that issue. And then we could go ahead and uncomment the section and rerun our training. While the training is going on, we are going to create this method. So this method, basically, we're going to copy from this. So here we should add a cell. We add the cell. And then we'll define this method, which we'll call train, or let's call it neural learn. So we'll call this method neural learn. And our neural learn method, we are going to take in a training data set. So we have train data set and then our validation data set. We could also get in the model. So we have the model. We could pass in the number of epochs. Let's have that here. So it looks like the model fit, which comes with TensorFlow. So here we have the number of epochs. And then after the model, we have the loss function, metric, val metric, and that seems okay. So here we have that. We then have this call. So here we just have neural learn, and then we pass the model, learnet model. We pass the loss function, we pass the metric, we pass the val metric, we pass the train data set, we pass the val data set, and then we pass the number of epochs. So all we need to do now is just run this, and then our training process is going to start. Getting back to the training here, you see how this training loss, you see we have the training loss, we have the accuracy, we have the validation loss, and we have the validation accuracy. Let's stop this, and then we could even take off the cell. Let's take off the cell. Okay. And then we have that cell off. Let's delete that cell and then focus on this. So now we have our neural learn, which takes in the model. So here, as you could see, we had this optimizer, we had the metric val, epochs. Let's get back to the optimizer. Let's add the optimizer here. So we should have After this loss function, metric, and then let's have optimizer. There we go. Now after the metric here, we have our optimizer. Looks fine. Let's run this and this. Loss function not defined, so let's scroll up and we have this custom BCE. So let's just put out the custom BCE right there. Custom BCE. We run that. Training is now complete, and here are the results we get. You now know how to create your own custom training loops and make them run in graph mode. Thank you for getting right up to this point, and see you next time.